Welcome to Lesson E of Unit 7. We are roughly doing Lesson 7-6, but only kind of, so don't worry about it. Just follow what's here. If we could hop in the Wayback Machine, and if I could find a cool effect in iMovie that would be kind of shimmery and make us feel like we're going back in time, I would use that right here. If you look at this sequence, 2, 4, 6, 8, 10. 2 is what we call the common difference because we consistently have to add 2 each time to get the next term in our sequence. And this is what we called an arithmetic sequence. Now, flash forward again. Take a look at this sequence, 3, 12, 48, 192. 4 is what's called a common ratio because you have to multiply each term by 4 to get the next term, and because we are multiplying, this one is a geometric sequence. I am looking at page 453 in your book, Activity 1, and I would like you please to complete number 1, 2, and 3, both parts A and B. So your answer should look something like this. The common ratio in the first sequence, you multiplied each term by 2. The next 3 terms in the sequence are 32, 64, 128. Number 2, letter A, the common ratio is 1/4, and here are the next 3 terms. For number 3, the common ratio is -3, so be careful here because this means you're going to have, in this case we start with a positive number, and the next one's negative, and then the next one's positive again. Let's get a little bit of vocabulary written down. Please write down everything for common ratio, the fixed number used to find terms in a geometric sequence. All right, geometric sequence, I don't know that you need to write down this whole thing. It's rather long. Geometric sequence is a number sequence formed by multiplying a term in the sequence by a fixed number to find the next term. I would be happy if you gave me an example of a geometric sequence and gave me the common ratio so I knew that you knew what you were talking about. The last vocabulary term I have for you is exponential function. That is a function that follows a geometric sequence and has a positive common ratio. So, here's the form that our exponential functions will use, and in this form a is a constant, so for example it will be y equals 3bx. B is positive every time, and b is not equal to 1. We're going to spend a little bit of time working on what this means. Get this definition and all the requirements written down in your notebook, and then we'll go back and work on it. So this is the box on page 447 in your books, and it's giving you 4 different examples of exponential functions. All 4 of these functions fit this format: y equals a times b to the x, a is never equal to 0, b is always positive, b is never 1, and x is a real number. This side we've got a is 1 or a is -1 down here. B is 2 in both cases. And when a is positive, our graph curves upward. When a is negative, our graph curves downward. Come over here, we have b is in between 0 and 1. b is greater than 0, but less than 1. And then this one, again, we have a is positive 1. Down here, a is -1. So when we do that, our graph flips this way. Or negative, our graph flips this way. Take a look at these 2 pictures until they make a little bit of sense to you. I want to take a look at one more kind of basic thing before we move on to doing some math. This is the box at the very beginning of 7-6. I'm still on page 447. These are two different plans for a soccer team to practice. Plan 1, 5 minutes today, 6 minutes tomorrow, 7 minutes the day after that, and so on. Plan 2, 1 minute today, 2 minutes tomorrow, 4 minutes the day after that, 8 minutes the day after that. The question is, which plan gives your team more total practice time over various number of days? As you can see, at the very beginning, plan 1 is more, but very quickly, plan 2 catches up and then gets much bigger. Plan 1 is an arithmetic sequence because we increase by a common difference. Plan 2 is an exponential function or a geometric sequence because we increase by a common ratio. We multiply. Problem 1, they actually give you some very helpful wisdom. I'm on page 448. We're going to just kind of walk through this together. Take a look at this problem. They want to know if this is an exponential function, and how do you know? Well, they show you down here. I wish they'd shown it this way when we were doing linear functions earlier, but anyway, we are adding 1 each time to the x value, but to generate our y value, we're multiplying by 3 every time. So the fact that we are we show adding between the x values but multiplying between the y values shows us this is an exponential function. There's a constant difference between the x values and a constant ratio between the y values. I think that's a helpful explanation. So problem B in that same section, page 448, they give you a crazy, wordy, complicated explanation, which is true and correct, but they just showed you how to figure this out with tables, so go ahead and use a table. They gave you the function y equals 3x squared, and if we use an arithmetic sequence for x, in this case we're going up by ones, do we have a geometric sequence for the y values? No, we don't. So this is not an exponential function. Done. So in case you hadn't guessed by now, graphing is kind of an important part of algebra. So we are going to take a look at problem 3, page 449. They give you the function y equals 3 times 2 to the x, and they want you to graph it. Well, it's easy. Just make your table of values. Here are your ordered pairs, and then plot them. Now, when you have a function with an exponent in it, you're not going to have a straight line. You're going to have a curve. So you're going to plot your points very carefully, and you're going to connect them with as smooth a line as possible. Give this a try. Just, you know, I kind of like how this one is positive 0.5 and that one's negative 0.5. So go ahead and graph both A and B, and then let's check back and see what we've got. All right, letter A. Why don't you guys help me finish this up? So I started by rewriting my equation. Point of mathematical thinking. Is this function the same thing as 1.5 to the x? If I think, oh yeah, I can simplify this by multiplying 0.5 times 3, and yeah, just think through that. Oh, there's Reggie the dog. Okay, then I started, by the way, the answer is no. So if you did this, you're going to have to go back and redo your math. Then, with a line, if you figure out 2 points, you have a line. If you figure out 3 points, your line will look neater if you're working freehand. With a curve like this, I want you to have at least 5 points. And as you can see, I started off with small numbers for x, but then I thought, oh, let's see what happens if we go negative, and so I added a few more numbers. I'm going to go take care of that barking dog. I'll be right back. Okay, dog is outside. So at any rate, I used a variety of x values. I didn't get really big, but I did make sure to put in 0. I did make sure to put in -1, -2. I'm sure you guys are going to check this math for me because who knows whether I got it right or not. And then notice when I chose to do my graph, I never got to negative y values. And my numbers, a lot of them are pretty small. So the scale that I used on my graph is kind of large. And when we go to graph it, it's going to look a little bit like this. X0. Do you see how fast it gets a lot bigger? 3, and already at 3 I'm off my graph. So at -1, we're at the y value of not a lot. I'm going to put this dot right about here. And then I will try to artfully swoop my lines. That's not bad. There's what our graph looks like. So for letter B, I didn't really redo the math, I just kind of used my brain. If all I'm doing is multiplying by a -0.5, then that should mean, I believe, that my y values are just all going to be negative instead of positive. So I am using mostly quadrant 4 of the graph down here. And it should look a little bit like this. If x is -2, y is negative just barely above the line. If x is -1, y is going to be still just barely above the line. When x is 0, y is -0.5. When x is 1, y is -1.5, and so on. And then again, with the artful curve, there you go. If I had plotted letter A and letter B on the same graph, they would be mirror images of each other. All right, your classwork. I'm kind of piling this on, but some days I've noticed there's a certain person who finishes his classwork in about 5 minutes, or maybe it's her classwork, and I want to make sure everybody stays busy. So see how long it takes you to do those problems, and that is all for today. Nice job.